Hello, Sandre here. Now, before I begin with this very first lecture that I ever upload to YouTube, I want to tell you guys a couple of things. Dare I say, I will make sure that these lectures are going to be some of the best ones ever uploaded to this website, because I take a lot of pride in my work. I always put quality over quantity, and it's a matter of principle for me. I'm uploading this series of me teaching high school physics because, well, I work part-time as a high school teacher of natural science. I have everything between physics to chemistry to biology and mathematics. I will also take the opportunity to upload lectures in university-level chemistry because, as most of you know by now, I study chemistry at the university. So expect lectures about organic, inorganic, analytical, environmental, and atmospheric chemistry on the university level. However, this series about physics is going to be on the high school level, because that is the level I'm actually, well, qualified to teach. I will never step outside of my bounds. Eventually, I'll get around to making a series about high school chemistry as well. Don't worry about that. I will also make a series about high school biology. But when it comes to chemistry, for the moment, I'm going to stick to university level. Just because, well, it may sound strange, but it's actually going to be less work for me. Expect a very high quality from these lectures. I cannot guarantee how often I'm going to be able to upload these lectures. I'm going to try to upload at least one lecture per week. But keep in mind, what you may lack in quantity, you will have in quality. In these lectures, I will also show you tasks that I expect you to try and solve. And if you can't solve them, don't worry. I'm going to show you how to solve these tasks that I'm giving you. So you don't have to worry about that. Now, for this first part in this series about high school physics, there's not going to be any tasks. This is just going to be an introductory chapter, if you will, into the history of how physics really started. Now, before we get on with this, let me also just ask you very kindly that if you've ever felt like donating to me on Patreon, I would greatly appreciate it. I have 3 patrons as it is right now, which, I mean, that alone to me is quite amazing. I'm very thankful for that. And it is nice to know that, considering that like I said, I study full-time, not the easiest subject that I'm studying, by the way. Chemistry can be quite hard. And the fact that I also work part-time as a high school teacher, as well as having a dog to take care of and other obligations in my life, finding time to make videos here on YouTube as well as high quality videos, yeah, it's not the easiest, let me tell you. So if you would find it within you to donate a little bit to me on Patreon, I really would appreciate it. Now, keep in mind, I've been doing this years before I even got a Patreon, so even if people don't donate to me on Patreon, don't worry, I'm still gonna make these videos just because it's a hobby of mine. I enjoy doing this. I enjoy teaching people. That's why I'm doing teaching as a profession to begin with. I have the donations on a per video basis. Now, don't worry about that, by the way, because I charge max 2 videos per month. So what that means is, let's say that you sign up to donate $3 per video. You're never gonna donate more than $6 per month, in other words. So, don't worry about me spamming you with videos or whatever. It's not gonna happen. I charge max 2 videos per month on Patreon, so don't worry about that. Now, the reason I have it on a per video basis is because, when you have a Patreon on a per month basis, I just don't like the idea of getting donations without making videos a certain month. Like, there have been months when I haven't uploaded a video because I've had other stuff to think about in my life. And, well, I just wouldn't feel comfortable with getting donations when I haven't, actually put in the labor, if you will. So by having it on a per video basis, I'm forced to make, at least one video per month. So it's actually to benefit both you and me, really, as to why I have it on a per video basis. Anyway, I think I've been rambling for long enough. Let's begin. Topic: History of proto-physics. Course: High School Physics. Level: High School. Part 1. It was in ancient Greece that they first started to ask very basic questions about the world, without necessarily seeking answers in mythology. The Greek philosopher Thales from Miletus, who lived between 624 to 535 BC, believed that nature was at its core very simple, and he also wondered if maybe everything is made out of water. Empedocles, who lived between 483 to 424 BC, regarded the world as being made out of 4 elements. You may know these already: earth, water, air, and fire. Now, there are multiple explanations as to why the Greek philosophers believed the things that they believed about the world's origin and the basic natural laws that they observed. However, as great thinkers as the ancient Greeks were, their ideas never matured into a proper science that we have today. Maybe if their civilization had lived for long enough, it most certainly would. But alas, it wasn't meant to be. But one thing that's very clear when it comes to the ancient Greeks and their ideas about the world is that they merely thought about things. They almost never performed any experiments. It wasn't until the 1200s that Christian Europe once again made contact with the Greek ideas of the past. Many of the Greek writings were then translated to Latin. Aristotle was one of those philosophers in this time who were sort of rediscovered. And all the way until the 1600s, Aristotle, who lived 384 to 322 BC, was the great natural philosopher who had the highest authority of European thinking. His views of natural philosophy was even brought up in the church dogma. Aristotle is very important in the history of science, not because he created science, but because he was one of those Greek philosophers who laid the groundwork to modern science. Aristotle has often been named as the one who really properly created something called logic. Logic is about rules for thinking. It's a way to help us come to so-called correct conclusions about the world. However, as great a thinker as Aristotle was, he had some ideas that were plainly wrong, and would in his lifetime easily been proven wrong had the Greeks simply adopted the methodology of doing experiments. Aristotle, for instance, believed that objects that are twice as heavy as another object fall to the ground twice as fast. This is simply not true. Galileo Galilei, who lived between 1564 to 1642, is often called the father of experiments. He's called this not because he was truly the first one in history to properly do experiments, not by far, but he was the first one to routinely do experiments the way he did. There are earlier cases of experiments that actually, even by today's standard, cut the mustard, if you will. An example of an ancient Greek philosopher even, Eratosthenes. He had heard from travelers about a well in Syene, now Aswan in Egypt, with an interesting property. At noon, on the summer solstice, which occurs about June 21st every year, the sun illuminated the entire bottom of this well, without casting any shadows, indicating that the sun was directly overhead. Eratosthenes then measured the angle of a shadow cast by a stick at noon on the summer solstice in Alexandria, and found it made an angle of about 7.2 degrees, or 1/50th of a complete circle. He realized then that if he knew the distance from Alexandria to Syene, he could easily calculate the circumference of the Earth. But in those days it was extremely difficult to determine distance with any accuracy. Some distances between cities were measured by the time it took a camel caravan to travel from one city to another. Eratosthenes hired bematists, professional surveyors, trained to walk with equal length steps. They found that Syene lies about 5,000 stadia from Alexandria. He then used this to calculate the circumference of the Earth, and he calculated that the circumference of the Earth was about 250,000 stadia. Basically, he calculated the circumference to be between 24,000 miles and about 29,000 miles. The Earth is known to measure about 24,900 miles around the equator. So that Greek philosopher is definitely a good example of someone who did a proper experiment long before Galileo. But like I said, Galileo was the one who did these types of experiments on a regular basis. That is why he's called the father of experiments, which would eventually help proto-physics mature into modern physics. Galileo tested the ideas of movement from Aristotle by dropping a bunch of materials from the Leaning Tower in Pisa. He discovered that they fell roughly equally fast. This obviously meant that Aristotle was completely wrong. A major breakthrough was made by Isaac Newton, who lived between 1642 to 1727. He wanted to further develop the ideas of Galileo, using what was known about planetary movements, many ideas of which came from Galileo. He came to the revolutionary conclusion that the very same force which makes an apple fall to the ground is also what makes a planet go in orbit around the sun. However, the idea that Isaac Newton came up with gravity by studying an apple falling to the ground is most likely false. Newton understood that using a term called mass, he could explain what would seem like completely different phenomena into one single natural law, Newton's law of gravity. The laws of physics are the basis of everything in nature. Physicists try to describe the basic connections in nature, all from the biggest to the smallest, from the riddles of the universe to what's inside the actual atomic nucleus. Physics is more than a way to describe nature in. It's also a method to attain knowledge. We often start with claims about reality, so-called hypotheses. With a good hypothesis, we mean one which we both consider to be likely and one that is also falsifiable. In physics, a hypothesis is deemed false if we, in an experiment, are able to disprove it. Then it has to be rejected. If we fail to disprove the hypothesis, we say that the hypothesis is strengthened, meaning that it could be true, and the likelihood of it being true has by default increased. If a hypothesis resists being disproven over and over again, we might take it to the next level. The method of utilizing hypotheses and hypothesis testing is called the scientific method. It's a systematic way of answering nature's questions. We ask by doing attempts, and we observe what happens. That way, we will see if the answers that nature gives through our observations are in line with what we expect from our hypothesis. Another demand that we have out of something being scientific is that the attempts we are going to do have to be reproducible. In other words, others must also be able to do the same attempts or experiments with the same results. Imagine being outside a very cold winter day. How would it feel on your skin to touch a piece of foam plastic compared to an iron rail? Which one would feel the coldest? Despite the fact that the iron rail would feel colder than the foam plastic, if we were to measure their temperature, they would have the same temperature as the ambience that they're in. Basically, if you have minus 20 Celsius outside, they would both show to be minus 20 Celsius, even though, again, the iron rail would feel colder to the touch than the foam plastic. Since we can't trust our senses, we need to regard nature through simple measuring instruments. We measure temperature with a thermometer, not by putting our hand to something. You simply can't trust your senses for scientific research. An artist can express himself with the draw of a pencil, a writer with word. Physicists use mathematics. Now you could say, When an apple falls to the ground, you get the distance it traveled by multiplying the apple's acceleration with time squared and both of them divided by 2. Or you could simply just write the following: s equals g times t squared divided by 2. You could also represent this graphically. Mathematics is far more exact and effective than words, and mathematics is the language of physics. Keep in mind though, physics is not the same thing as mathematics. This will become apparent later on in this course. There is a tale of a man who, when traveling by train in southern France, happened to find himself sitting right in front of Pablo Picasso. After a moment, the man asked, "I'm sorry, are you Pablo Picasso, the famous artist?" Pablo responded, "Yes, it's true, I am Pablo Picasso. Can you explain to me, why do you not paint reality as it looks?" Pablo responded, "I'm sorry, I do not understand. Reality as it looks. How does reality look according to you?" The man took out his wallet, opened it, and grabbed a photograph and showed it to Picasso. Picasso asked, "Okay, and what is this you're showing me?" The man responded, "That's my wife." And Picasso asked, "So that's what she actually looks like?" The man responded, Of course that's what she looks like." Pablo responded, "But isn't she very tiny and completely flat?" All jokes aside, Pablo, if this story is true, which I doubt, but if it is true, he has a good point. The photograph that the man showed Pablo Picasso was simply a representation of his wife, the way she looked from the certain perspective of the camera at a certain point of time. But the format of the representation of his wife is not the same as his actual wife. The image is not actually what she looks like, only very close to what she looks like. In physics, we make great simplifications when we need a representation of reality. These simplified descriptions are what we call models, and we hope to capture the part of reality that physicists are interested of. Sometimes, though, people forget that models are just models and talk about them as though they are reality. Thank you so much for listening to my first lecture in this series about high school physics. The next installment is going to be about how physicists see the world. I'll see you then, guys. And again, thank you. Take care.